We're continuing on with our macromolecules and enzymes unit. Our next learning target 2, students will be able to identify the reactants and products of a chemical reaction and show how they break down and build molecules. Okay, so we'll be talking about reactants and products. We'll be talking about chemical reactions that join small molecules together to build large ones, or to break large molecules down into smaller ones. Now, when we look at chemical reactions, these change substances into different substances by breaking and forming of chemical bonds. So we're just kind of rearranging those bonds by breaking them and reforming them so that we can form different molecules. A reactant, okay, is a substance changed at the beginning of the reaction. It's what is reacting, so it always comes before the arrow. So if you look down here in this chemical reaction, what are your reactants? Well, it would be the carbon dioxide and water. Okay. Products are substances made by the reaction. It's what is being produced. That's why it's called a product. It comes after the arrow. So here's your product right down here. Because you're always looking at where the arrow is, anything that comes to the left of it, in front of it, is your reactants. Anything that comes after it is your product or products. All right? So always keep that in mind as you're looking at different chemical reactions. So we're going to do a little bit of practice here. What are the reactants and what are the products? Okay, well, first of all, let's spot where our arrow is. If you see your arrow is right here, anything that comes in front of it would be your reactants, because they're the ones reacting. So your methane and your oxygen. Whatever comes after the arrow are your products, because that's what's being produced. All right, so always be, first thing, if you're asked what are the reactants and the products, find that arrow, because that's the easiest way to tell what are the reactants and what are the products. Chemical reactions transfer energy. It means that they either release it or they absorb more energy. And that energy is transferred by the building and breaking of those chemical bonds. Now, activation energy is the energy needed to start a chemical reaction. Okay? It's the amount of energy that needs to be absorbed to start a chemical reaction. So the analogy they're using is this person pushing this boulder up a hill, or ball, whatever it is. The energy needed to push it to the top would be the activation energy. Once it gets to the top, it can kind of roll down on its own. It doesn't need any more input of energy. Now, when we talk about chemical reactions, we can pretty much break them down into two types of chemical reactions: synthesis reactions and decomposition reactions. We call the synthesis reactions dehydration synthesis. This is the term I want you to, the name for these processes, chemical reactions that I want you to learn. When you think of dehydration, what do you think is happening there? We're like removing water, right? We're drying out. Okay, so keep that in mind. Synthesis means to build. Okay, so keep that in mind as far as what that term means. So what we're doing in a dehydration synthesis reaction is smaller subunits are joined together. Okay, that's the synthesis part. You're building something to form a large molecule. Water is released. That's where that dehydration comes from, because you're releasing the water. That's why we name it that. So when we join smaller subunits together, synthesis, to form a large molecule, we are releasing water in the reaction. So this is a dehydration synthesis. An example could be when we're trying to join two glucose molecules together to form maltose. That would be an example of a dehydration synthesis. In order to get those two molecules to fit together, you actually have to remove the hydrogen from one of the glucose molecules and a hydroxide group, the OH group, from another one. Well, when you join those OH and H together, you get H2O, which is water, and so that's the water that's being released. In a decomposition reaction, we call that a hydrolysis reaction. Well, again, let's break down this word here. Hydro means water. Lysis means to break apart. To break down. Okay, so in this one, you're taking a large molecule and you're breaking it down, that's the lysis, into smaller subunits. In this case, water is added. There's your hydro to the reaction. So now, since we're taking a large molecule, breaking it down into smaller molecules, guess what? They're going to need the H and the OH ends put back on their respective molecules. And so we have to add water into the reaction this time, that H2O, so we can get a hydrogen ion to go on one of the molecules and the hydroxide, the OH, to go on the other molecule. An example of this would be if you were breaking down starch into several glucose molecules. So you're taking a large starch molecule, you're breaking it down into smaller molecules. That is hydrolysis. So these are the two reactions you need to know: dehydration synthesis and hydrolysis. So let's look at these reactions here and see if you can figure them out. And they're kind of divided in half this way. So I'm just going to draw a line there in between the two. Okay? So here's this large molecule. What's this showing here? This is H2O, that's water. And they're drawing an arrow in. Okay? So they're adding water. Okay? Because that arrow is going in. They're taking one large molecule, they broke it down into two smaller molecules. So this one, if they're adding in water, that's hydro. And if they're breaking it into two smaller molecules, that's lysis. So this is a hydrolysis reaction. In this one, they're taking two glucose molecules together to make sucrose. I don't know that makes sucrose. I think that makes a different molecule, but that might be an error. But anyway, they're taking two smaller sugar molecules to make a disaccharide. But look here, now where the water is, the arrow is going out. So water is released. Okay? So two small molecules being joined together, that's a synthesis reaction, but they're releasing water. So this one would be a dehydration synthesis. Okay. Now we can also classify chemical reactions in terms of whether they absorb more energy or release more energy in the reaction. If it's an exothermic reaction, it releases more energy than it absorbs. Exo means out, so it's releasing more. Excess energy gets given off as either heat or light. And so some of the examples are cellular respiration, where we actually release more energy, more ATP at the end. Fireflies, when they're blinking and giving off that light energy, that's an exothermic reaction. Of course, probably your favorite from the summertime around the 4th of July, fireworks are a good example of an exothermic reaction. Endothermic reactions absorb more energy than it releases. And endo means in, so it's absorbing more energy. So it's showing you a picture there of an ice pack. It's absorbing the heat energy, It's being radiated from the injury in your arm, the inflammation from your arm, and it's absorbing that into the pack. And photosynthesis also absorbs light energy. When plants take in light energy, they're absorbing that in, and so that's an endothermic reaction as well. So when we look at this in a graph form, this may look a little confusing, but what I want you to look at is here's your potential energy along the y-axis. X-axis is the reaction in process. If you look at this, look at how much energy the reactants have. Look how high up they are on this graph. When you look at the products, look at how low they are now in terms of energy. That means if a product has less energy than the reactants have, that means somewhere along the line they lost energy, correct? And so when we look at this, here's where we started. We lost all of this energy right here, okay? That makes this an exothermic reaction because we're releasing that energy. If it's endothermic reaction, remember that's where you're absorbing more energy. And here we have the reactants down here, how much energy they have. Look how much energy we ended up with, how much the products had. That means we had to have absorbed energy in order to have a product that has more energy than the reactants. So that's why that is an endothermic reaction, because it absorbed more energy. So don't get frightened by these graphs that they like, oh, this is just so confusing. Always just go to where are your reactants, where are your products? Do the reactants have more energy than the products? That means we had to have released some energy. That means it's exothermic. If your products have more energy than your reactants, that means we had to absorb energy.